Hey class, how you doing? I hope you enjoyed the relatively short week of classes, right? No, we didn't have school on Monday. Actually, I couldn't really do anything on Monday. I was surprised how many things were closed. But anyways, so this is the article I chose for this week. Has to do with computational chemistry, and chemistry is a wide subject, and there are lots of things you can do in studying chemistry, and one of them is computational and also theoretical. If you're someone, a theorist, it means you don't do actual experimentation. I'm not a theorist, I'm an experimentalist, and most scientists are experimentalists, but there are a few theorists. And computers, not all theorists use computers. Einstein was a theorist, and but I mean, obviously, didn't use any computers. But computers are getting bigger and stronger. Well, bigger. This one's pretty like size. It's big, but I mean big is in terms of computational power. And this article says this is what it means when you have a really strong computer and what kind of things you can do chemistry wise and with it. It touches on a few things. I mean, you think about computational power. I mean, you think about, oh, what kind of sweet, cell phone and what kind of movies can I watch? Well, there's other things that you do with computational power, and one of them is science. And this article talks a bit about things. Let me tell you about some of the new things that go with that. And if you want to know, James Webb Space Telescope that was just launched, and Large Hadron Collider that is the biggest collider in the world right now. It's in Europe, and they found the Higgs boson. It seems to support the general model for physics, which is not chemistry, but these are very big, expensive thing, especially the Large Hadron Collider. That's a very, very expensive piece of equipment. It's huge too. So, and this graphic, when I first looked at it, it took me like I had to look at it a few times to get this. So if you see this little corner here, this breaks out in this corner here, and then this little sliver here breaks out into here. So you can see a standard personal computer compared to an Xbox. Oh well, Xbox even there, series there, and goes over here, and the supercomputers, and you can see how this exascale computer is going to range, how much bigger it is than your standard personal computer, like the one I'm recording this video off of. And so what? Why do we care? Well, one of them is medicine. So you can see this is an image of the Delta variant of the SARS-CoV-2 virus, and you can see, and it mentions this in the article, they bunch atoms together, and very frequently when you do biochem research, you look at it, you look at the protein structure in terms of where the just the kind of the backbone of the proteins. So a lot of you have other types of structures, alpha helices, beta sheets, for instance. And so this is what that looks like for me. Is that it's very common for biochemistry to do that. And if you look at chemical systems, and it talks about this a little later on in the article about time scales. I mean, so if you have an atom, you move it a little bit, move it a few femtometers, a few picometers, or something like that, and then you have to recalculate a bunch of wave functions and stuff, because you have to calculate how the electrons are with the different nuclear conditions. So this could consume a lot of computational power to do that. It talks about that as well, and also for dynamic simulations. So for things like looking at reactivity of metals and alloys, they group them into smaller groups of atoms, and this is a huge amount. I mean, like it's real easy to model an atom on a metal surface, and if it's evenly spread across, if you have a single atom on 2 million, and then 2 million atoms of metal, and you have a single lone atom, or you have a single defect in this metal structure, it's much more difficult to do that computation than it is a very even spread. So these kind of computations can look at the very, very uneven spread and more close to lifelike simulation, to more lifelike. And I said simulation. There is, well, it does mention this later on in the article that that well, one of the things my father always said: the theories provide, the experiments decide. So, meaning that we're in the age of reason. We don't deal with pure theory. We deal with real data. That's what we do right now in the age of reason. We deal with real data. If we don't have direct connection to experiment, then we're just playing very large video games. So this has to deal with something in real life. And although we're doing more and more research with drugs and with therapeutics using, especially with COVID-19, but we still have to go through the rigorous FDA sort of cycle for approval and stuff. We're not gonna like, oh, computer says it's good. That's I've given everyone their shots. No. We still have to do some actual experimentations to see if it's safe and effective. So we're not there yet, and I don't know if we ever will, to be honest with you, because one thing when you do calculations, I mean, they can be completely wrong. I mean, uh, and if you're trying to predict a certain property, I mean, you have to finesse it. We're not there yet that we understand everything that we can just put into a computer and let it rip. But we're getting better. We're getting better, and we're getting pretty good at it. So, and something at the end of the article I thought was kind of funny, and they used to joke around it. I went to Berkeley for grad school, and there you have the advanced life source. So the ALS, they called it, the advanced light source, and it was open. So this computer is open, so you can run it. If you want, you could submit a proposal. So anyone can submit a proposal and then have it done here. And they mentioned that jokingly, and that is a joke kind of in these open sort of places. I mean, is someone going to come off the street and put in a proposal? And no one has. I mean, so maybe if you want, if you could, go ahead and put a proposal forward. But I mean, it has to be a good proposal, of course. There's a committee that decides what's going to go forth and how much time to assign you. So it's and it has to be for a reason as well. And I mean, like a drug company said, like, we want to do all our research on this computer. No, it has to be something for the greater good and publishable. You can't publish your financials or something like that, or whatever you're going that's confidential. So that but yeah, anyone can put forth here. So I remember reading that. I thought I kind of chuckled at that. So, anyways, I know I'm going long these videos. I told you I'd make them short, but I'm talking a lot. Sorry about that. This is an interesting article, and I thought I'd talk a little bit more about it and give you a little bit of the background on this. So, and of course, with all my correspondences, I mean, I'm concerned about your well-being, your mental health, your basic needs. So, if you're finding yourself that you have any situations that you're having a hard time with any of those, let me know. And also academic issues, this class, other classes, I will do what I can to help. So keep me in mind if you find yourself in a tough situation. So I'm going to stop talking. I know I've gone too long, but I hope you have a wonderful rest of the week and the weekend, and then I'll write you again on Monday. So aloha for now.